Okay. No, so let's go on. Last week we stopped when discussing constructivism. I remind you that we actually we used standard format for talking about say so-called foundational crisis in philosophy of mathematics, or in mathematics itself, in 20th century. And we distinguished in the standard way between three, say, positions in the foundations, one of which was logicism, represented mostly by Gottlob Frege and Bertrand Russell. And the idea of logicism was to reduce, in some sense, mathematics to logic, even if I try to stress that actually this notion, the borderline between mathematics and logic, was never set precisely, and it is still debated. So when we're talking about such a reduction, it should be understood, say, very flexibly, because surely it depends on what you count, what you qualify as logic and mathematics, right? No, anyway, I think it's a reasonable description. Then we discussed Hilbert's so-called formalism, which is a much more sophisticated position. In a sense, as far as I can see, it also accepts some sort of primacy of logic, right? Just think about Hilbert early work of 1899, Foundations of Geometry, where he introduced this modern version of axiomatic method. Even if this particular version, we could call it kind of semi-formal. But on the other hand, this is exactly the version which was and still is influential in mathematical practice, because so-called fully formalized, at least in today's language, that means all symbolic, right? That requires that we actually provide exact logical syntax, logical calculus, right? And only then somehow apply it for making certain theories. But anyway, exactly this kind of construction, that logic is supposed to be fixed first and then somehow used for building mathematical theory, is say it's a common point with logicism, right? It's not full logicism, because Hilbert does not try to say that mathematics is logic. However, he shares the idea that foundations of mathematics should be logical in some sense. And if you think, for example, about, say, Zermelo-Fraenkel set theory, right, which is a set of axioms, and it is a set of axioms formulated with a particular logical calculus, and namely with classical predicate calculus, right? So this classical predicate calculus is a foundation of set theory, and then we use this calculus to formulate certain axioms, and then we are looking for models of these axioms, and so on. That's how it works. And also, it's included very important feature. It is what Hilbert called meta-mathematics, or proof theory. Actually, he kind of equated meta-mathematics and proof theory. Is a possibility to study syntax of a formalized mathematical theory and study it actually by mathematical means, and that's what he called meta-mathematics. That he hoped could be kept very minimal, even finitary in some sense, and thus in his idea, it was to serve again as a foundation of mathematics. And that's what is called formalism. And finally, we discussed intuitionism, or actually later, something very similar. Sometimes they distinguish, but anyway, it comes very closely together. It was called constructivism in foundations of mathematics, right? And this intuitionism and constructivism was represented or was founded by Lutz Brauer, who was Gilbert contemporary, right? And that's I gave you last week example of example that demonstrated, I hope, this kind of tension between constructive and non-constructive reasoning. Formally speaking, it reduces to, or say, comes down to issue whether or not law of excluded middle is accepted as valid logical principle or not. However, in fact, there is much more issues than that. And this view, it's already kind of later view. I'll explain you now. Later view on, say, intuitionistic mathematics. Because Brauer actually, he was a person who tried to contribute actually both to philosophy and mathematics. His PhD, his thesis was rather philosophical than mathematical. And as a philosopher, he developed, his philosophy hinges very much on Kant, which is in a sense maybe typical. So unlike people like, say, Bertrand Russell, he was not so revolutionary in philosophy, right? So Kant was accepted authority at that time. However, he tried to realize certain Kantian principle in context of new mathematics, and he did it in a very original way. Moreover, he was a working mathematician himself, right? So in the literature, you find a lot of, how say, pejorative expression towards Brauer philosophy. Probably they are partly justified. No, sometimes it's even described as mysticism or something like that. And no, probably Brauer himself gave certain, he's responsible partly for that. However, I think he had also some philosophical ideas which were strong, or positions, but quite rational. For example, he simply, unlike both Hilbert and say Russell, he did not by this idea say that foundations of mathematics should be logical. Okay, so he rather considered logic as a part of mathematics, rather than mathematical theory being something based on logic. You see, and I think that's interesting and important controversy, which I don't think it's definitely resolved, and so it may be interesting even today to think about this. Yeah, and the related point in Brauer was that he didn't believe that analysis of language actually is so important. Because again, if we think, particularly if you think about Hilbert's formalism, right? It's all about language. It's all, or even formal language, right? So if we now thinking about Hilbert's program and its mature form, right? When you're supposed to formalize theories completely with certain symbolic language, then somehow language becomes the most important thing in mathematics, right? How you write down your theorems. Of course, also language is not only syntax, but also semantics, right? So language consists of, no, if we follow another, this kind of tripartition, which was actually invented by American philosopher Peirce, Charles Peirce, but nowadays became quite standard. So he distinguished in the language three aspects, which are syntax, semantics, and pragmatics, right? Syntax is about, say, formal expressions, how they are built, about symbols, roughly. Semantics is about meaning, and pragmatics is about using language, okay? And there are, of course, all kind of intersections. For example, there is an influential trend in semantics that tries kind of reduce semantics to pragmatics. It's sometimes called meaning as use paradigm. And usually people see philosopher Ludwig Wittgenstein as kind of founder of this approach. Yeah, anyway, I just want to stress that the language is not just syntax, right? It's also at least about meaning, even if we now leave this question of use a bit aside. Right, but anyway, Brauer just disagreed that all this, how we express and communicate, say, mathematical contents, mathematical thoughts, reasoning ideas, he disagrees with that approach that we can somehow analyze all of that just by analyzing certain expressions, right? Formal or not formal. So he believed that actually mathematical objects are kind of mental constructions, and mathematical activity, mathematical thought and reasoning is a, say, mental activity. Yeah, that's true. He wrote things which are not so easy to interpret. However, I think that's, again, important intuition. That's important things that happen not when they are written down on a paper or now computer screen. However, important things happen in our minds. That was his, again, his intuition and his point of disagreement. Right, so he designed this so-called intuitionistic mathematics, which I don't have really time, and I'm not an expert. I know, yeah, actually I followed a semester of this mathematics when I was a student, but still it's very, how to say, singular, because it involves some specific mathematical concepts like choice, like sequence of three choices. So he had this intuition that as mathematical objects, we may have, say, infinite sequence, right? Equal or series. However, he did not accept, as we may say, constructivism, this idea of actual infinity. So he just disregarded this counter set theory that I recall Gilbert embraced, right, and called counter paradise. So he rather stick to idea of thinking in terms of infinity, but potential infinity, not accomplished actual infinity. Right, and for example, he considers such things, which has an important role in his mathematics, as a free choice sequence. So we say of natural number, you just form one natural number after another, and that may go without any specific rule, or it may come with specific rule. And then he tried to make that into foundation of mathematics, and say, including analysis, differential integral calculus. And important thing, of course, that working with such things indeed somehow does not admit, say, using excluded middle, right? So intuition again is that, say, if imagine you have a decimal extension for pi, and you don't have it as an infinite series, right? You just have a certain process, a computer, which computes one digit after another. And then if you ask, say, whether or not there exist, say, 10 zeros, one after another, 0, 0, 0 in this expansion, then you say you cannot apply excluded middle to that proposition, right? You can say what either as such 10 zeros exist in this series or not, yeah, unless you really computed it eventually, right? So so that's rather peculiar mathematics, interesting. Yeah, what he did. There are still some enthusiasts, but important thing that happened in this development was work of his student Arend Heiting. Probably you know about Heiting algebra, right? Let me share my screen. Yeah, this Arend Heiting. So this Arend Heiting, he made kind of, he was a kind of middleman, right, between intuitionism. So he was a disciple of Brauer. However, he started to find kind of bridge between his approach and, say, formalist approach, broadly conceived, right? So Brauer, because of this, say, philosophical ideas that language is not important in mathematics and that really mathematics happens in one's mind and not on paper, he actually, in a sense, was against the whole idea of formalizing anything, right? So he didn't think it's somehow relevant thing to do. However, what Heiting did, can you see my screen?
Yes.
Yeah. You see, no, so roughly speaking, he tried to formalize intuitionistic logic. And that's something that in Brauer's view was a sacrilege, blasphemy. Как это по-русски? Святотатство. So Brauer actually did not approve of these approaches, of these attempts by Heiting. However, what we know today as intuitionistic logic, right? Say, propositional intuitionistic logic is what originated in Heiting's work. And as I say, in many textbooks and papers, you'll find this kind of narrative that Heiting was first who somehow managed to extract some rational ideas from Brauer's crazy mystical intuition. I think that's wrong. That's wrong, because these issues, say, of whether logic is part of mathematics or mathematics not is part of logic or is the same as logic, right? It's still, I think it's quite a normal and issue to discuss. There is nothing mystical about this. No, anyway, these attempts by Heiting were, of course, very important. And there is a little book that actually became very famous. I think this is in English. It's was published in '56, called Intuitionism, and it's translated, by the way, into Russian. So you can. I think it's a very nice book indeed. So he explains something about this philosophy, but also introduces and explains this intuitionistic or constructive reasoning, say, formally. And of course, that's, in a sense, it saved this idea because no, I think it really, in real history, it so happened that this formalism, but very broadly conceived, of course, formalism, right, was a mainstream, and unless Haiting somehow managed to fit the whole idea of constructive mathematics and Lucianism into this mainstream, it certainly would be just forgotten and completely marginalized. I think so. Right. And by the way, there is a later paper, I think I already mentioned it last week, by Per Martin Löf. I think it's 2007. It's called Gilbert Brauer Controversy Resolved. So Per Martin Löf, he believes that actually today there is no longer controversy, but he refers not only to Haiting, but also, say, to his own work, which was also strongly motivated philosophically by Brauer's ideas, but not only by Brauer's, also, say, by Frege's ideas, who opposed very much Hilbert, who didn't accept this, say, Hilbert's notion of axiom, which is indeed very strange from, and even looks like misuse of the term, I would say, from a logical point of view. Because recall in Hilbert, axiom is something without truth value, right? That's, of course, sounds like crazy, or, as I say, misuse of the term. So Per Martin Löf basically he argues that, okay, even if language is not the whole thing, it's still important, right? And it's quite possible to somehow to implement these ideas also formally. And that's what he did in his version of type theory, that he himself, by the way, called intuitionistic, not even constructive, but intuitionistic. Term constructivism was popularized by several people in Soviet Union. It was popularized by Kolmogorov, by Markov, the younger Andrei Andreevich Markov, who was kind of founder of constructivist school in St. Petersburg, then Leningrad, and his pupil Nikolai Shanin, who died about 10 years already ago. Yeah, so these people certainly they didn't want to somehow commit themselves to any kind of philosophy of Brauer, and actually I think they officially, since it was a Soviet Union, they had to explain somehow that that's all perfectly squares with dialectical materialism and this kind of things, right? Yeah, so they just invented, or maybe not invented, but borrowed some this word constructivism. And basically, and I think the strong point of this Soviet school was that they actually realized that this whole topic is closely related to, say, computational mathematics, right? To theory of algorithms, which was also field where Kolmogorov and other people contributed a lot, right? So somehow they switched focus, say, from this philosophical discussion on language, not language, to more practical things and pragmatic things. And I think now, in historical perspective, we may say they were they were right, at least in the sense that this computational mathematics became very important, and because of importance of computer. And but that was started before the war, so in 30s, even in late 20s and 1920s, 1930s, where nobody really could predict this kind of how say emergence of computers. No, in a sense, they were also kind of father of computer science, right? However, I don't think that anybody could, how say, really predict that, say, in 70s and 80s, and at the turn of next century, computer will change indeed life of everybody. I think that was not really predictable, right? No, by the way, so Soviet school of constructivism is very important. And by the way, historically speaking, it's not completely studied, because a lot of things are in Russian. No, I say important things, of course, they are translated, they're internationally known. However, for example, here in St. Petersburg, there is an archive of a seminar on constructive mathematics, which is all in Russian. And I think nobody really, I think that could be, say, dissertation in history of mathematics, which so could be a lot of really interesting and internationally unknown details there. I looked a little bit. I was not prepared just to make it a big project for myself, but I think for maybe some of you, or I don't know, your friends, I think it's still, it will be very good international dissertation, because it's a kind of new material on topic which is already recognized as important. Yes, right. However, constructivism was not actually limited to Soviet Union. Another important figure is Bishop. I don't know, do you know about Bishop constructivism?
Sorry, about what?
Bishop. Now, I forgot his first name. I'll show you. It's American mathematician who also, Bishop, his name is mathematics. Errad Bishop, right? Right. So it's kind of American version of constructive mathematics, which I think also was more motivated kind of practically than philosophically. No, anyway, it was, you see, very influential in the 60s. By the way, interesting, and that was actually different in details, because also you should understand when someone says constructive mathematics, right? No, first of all, you should distinguish between, say, philosophical aspect and formal aspect, even if they are mutually related. They're related in the sense that, say, philosophical views motivate certain choice of formal principles, say, roughly in that way, right? However, and of course, these philosophical views are very actually different. It is spectrum of different view. It's not just one single thing, right? But even if we look into formal part, it's also diverse. There are many versions. There are small differences. There is so-called Markov Principle, like Markov Principle. Yeah, I think this one. Yeah, you see, it's internationally known by that way. So it's about first order logic, particular constructive principles. And there are many such things. So just saying that we use or not use excluded middle, okay, that's kind of basic, but it's not all. Okay, there are more specific principles and they actually differ. There are many versions. So for example, I don't know, this coming back to Bishop, I don't know, for example, whether he had any contact with with Russian school. So now today everybody say Russian school and him, but whether there was really exchange or they worked completely independently, which would be strange because in 60s, since still there was a rather vivid exchange usually. Yeah, so I think it's all open historical questions. Nobody really knows. So this Everett Bishop, he published influential foundation of constructive analysis, and that was also supposed not just like in the Russian case, it was not a book in logic, it was kind of practical kind of foundation. So he also hoped to make it as a kind of practical project. Yes. No, I must confess I know about Bishopless, so I kind of read through this book. Russian school I know a bit better. Yeah. No, at least you should. I think his widow, she's still alive, and I think I met her 2 years ago in Princeton Institute. So yeah. Yeah, no, okay. Now I'm supposed to give you an overview. Yeah. No, maybe a last thing about constructivism I want to say again. I think there is and that was somehow a specific point I tried to emphasize in my research, because no, if you like, there is an aspect of constructivism which I think it was somehow present, right? However, formally, until recently at least, maybe until my work, it was not really took into account, and that has to do with the following question. There is this intuition that constructive mathematics actually works with mathematical objects, right? Not just with the proposition. So it's not just about, say, deducing certain prepositions from certain other proposition, but it's about making certain constructions, right? That that may justify certain proposition, right? It's like in Euclid's case. I think when we had this, we looked into Euclid's Element. Remember that in Euclid we find problem in theorems, right? And even in theorems, when it's actually is about proving a proposition, typically we do kind of what usually called auxiliary construction, right? We should say in geometrical theorems, and that's procedure which is not logical in the usual sense, right? It's not about making conclusion from certain premises using particular inference rule, right? But that's about, say, drawing a line or something like that. Even already in Aristotle, we find that's actually, and that's actually, that was noticed by Kolmogorov also. So in of problems, calculus, Kolmogorov. Oh. Yeah, that's Yeah, you see, in 32. Oh. Yeah, you see, that's already English translation, and original was in German in Mathematische Zeitschrift. In 32, he published, Andrei Nikolaevich Kolmogorov published a paper titled On the Interpretation of Intuitionistic Logic. And actually, he suggested a, say, different interpretation. So that was already after Heiting published some of his papers, not that book, that was later, but some of his papers. And what actually Kolmogorov did, he say, no, there are many interesting things, but one of these that he actually provided different semantics for basically the same calculus known today as propositional intuitionistic logic, right? And he called it calculus of problems. You see, so kind of basic units would be not propositions but problems. For example, say conjunction of two problems would, right, instead of truth value, right, you have a solution in that case, in case of problem, right? And say conjunction of two problems is a solution that solves both problems and things like these. And probably you heard about so-called BHK interpretation of intuitionistic logic. Right? I can write it down. It's called or sometimes it's called BHK Semantics. BHK Semantics. No, you may Google it for intuitionistic, say propositional calculus. So BHK stands for Brauer, Heiting, and Kolmogorov. Yeah. No, I think the best way to think about implication. So if you have implication, right, P implies Q, and now think about P and Q as problems. So that's interpretation is that, say, solution of P also solves Q, for example. Right. No, and then it's actually related to concept of algorithm, because if we want to make precise what solution is, right? So one way to formalize solution is formalize solution as an algorithm, right? So constructive notion of say solution. That's how it works. But still, yeah, of course, this BHK is not really formal semantics; it's rather informal semantics, but there are various ways to make it formal. For example, Sergei Artyomov has a very nice paper of about 10 years ago, which actually reviews literature on that question also and makes some of his own suggestion. However, I think in all this literature, this how to say aspect of at least Kolmogorov's approach, I don't know how much it also applies to Brauer and Heiting. But however, at least to Brauer, I still quite sure it also applies. Less sure about Heiting. Was that part of solution, right? It's again, it's kind of construction. It's something which is done with, say, not propositional objects rather than just objects, rather than just propositions. And then you can, I kind of got also motivations to this idea in homotopy type theory, then I probably explain later. However, I think this idea does not require such even fancy things. It's very simple, right? That say in geometry we do something with triangles and lines and everything, and not just with propositions. And if you somehow ignore this aspect or say it's all just kind of heuristic, it's all context of discovery, it's all heuristic. However, at formal outcome, at formal presentation, we have only propositions and nothing else, then I think it's indeed gives us very impoverished notion of mathematics. And actually it makes all this formalization kind of, no, I wouldn't say irrelevant, but at least practically rather useless. Right. Yeah, okay, so probably I stop here just trying to describe this big trends as logicism, formalism, and constructivism. And next I come to, say, later developments. I have still 45 minutes. So, yeah, but maybe you have some questions on constructivism, then please ask me. Then I just continue. Yes. Евгений Светлана. Спросите меня.
No questions.
Okay. Yeah. No, okay, now I move on. Yeah, one thing actually which will be kind of between these two topics is this, that you see, on the one hand, if you look in beginning of 20th century, there is indeed very somehow hard philosophical debate, right? No, at least on Brauer's side, he believed that this mathematics which is not constructivism, it's just wrong, right? So in a sense, he simply did not believe his own fixed point theorem, which made him very famous independently on his efforts in, say, foundational mathematics and moreover, it's unrelated to his philosophical use. It just was very important theorem, just as this theorem about invariance of topological dimension. Those are just very important mathematical results. But I'm not sure about second, but I think it's also, it was not constructivism. But at least first theorem, it's a pure theorem of existence, so it's classical, and I didn't see he ever pronounce himself, but I think it's rather natural reconstruction that actually he did not believe his own argument, right? He didn't believe this theorem is really proved as it should be proved. So he, having this very strong philosophical motivation, he really wanted to revise all mathematics, you see. Right. No, I think Gilbert was less philosophical committed, I would say, but anyway, he, of course, his work in foundations was also important part of his work, and I think what he did in foundations at least was somehow coherent with what he did in other areas of mathematics. No, we are not talking about Russell because still he was not working mathematician, I would say. At least later, he just was a writer, a philosopher. Yes, but what I want to say that, say later, or at least today, I think this constructive mathematics, it remains important. However, in a sense, I think mathematical community normally does not fight philosophically, right? So we may develop constructive mathematics, which is now very much practically important because of computers and computer science. I come to that a bit later, right? But we may also develop classical. So what is important and somehow control it, right? Whether we use what kind of principle we use in each particular case. Yeah. And by the way, there is such a program. I don't know if you ever heard about this, called reversed mathematics. Reversed mathematics. I don't know, that kind of proponent of this program is Harvey Friedman. Harvey. I wonder whether he was really inventor. Maybe no, you may easily check it. At least he's the most known proponent. And reverse mathematics is a program, a research program that actually aims at studying, right, what kind of logical background is necessary, not only sufficient but necessary, right, for proving certain results. So, for example, now we think we have a proof of Fermat last theorem, right? However, it remains wholly open whether or not, in order to prove this theorem, whether or not the theorem is provable in, say, Peano arithmetic, right? Because the proof that is published involves a lot of geometry, a lot of various stuff. However, whether it is all dispensable in a sense, right, or not, it remains wholly open. Yes, and so trying to answer in such questions, but not only for Fermat theorem, you may ask similar questions for many mathematical results, and it's only in some few cases it's studied. And moreover, of course, there is specific, say, difficulty of this research program, because of course it may work only with formalized mathematics, right? Quite obviously. However, normally mathematics is not formalized. And then there are, of course, issues how to formalize it. And at least it is, again, my view that there is no canonical way to formalize it. And so you may roughly come to a situation when you have some piece of mathematics, but then you formalize it in different ways. And under some formalizations, you get some principle, and some other formalization, some other principle. So it's a rather, again, complicated thing. And so far open. Okay, so what I want to say next, say about kind of what happened next, right? Because these things happen in already 20th century, but say before the war, right? Hilbert's work of foundation began in even late 19th century. So Brauer also started very early, say in 20th century. So all this story about 100 years old, at least, right? Or a bit more than 100 years. So what's next? No, I should say I don't want to even try to overview all developments in mathematics in 20th century because there are just too many. However, I'll try to overview some developments, say, in foundations of mathematics. And then I also mentioned some related, say, philosophical ideas about mathematics. Okay, so I'll try to do that very quickly. So I think first thing I want to talk about is this project of known under the name of Burbanki. I already mentioned it several times during my course, right? And then I think you asked who is Burbanki. So Burbanki is actually a group of mathematicians which first gathered some before the war. Actually, you see Wikipedia says it's 34, 35. I think none of these really founders of Burbanki is now alive. So in the sense that Jean Dieudonné was, I think, the leading figure, even officially they didn't have kind of main or leading figure. Charles Erisman, also it's everyone is very, very important and interesting mathematician. André Weil, who died in Princeton. Actually, he died in Princeton. I was in the United States, so it was late 90s. Right. Now there is still, no, not very active, but alive, kind of next generation of this Burbankist. I know personally Pierre Cartier, who is still active, very much active. Right. These people were somehow gathered in École Normale Supérieure, or ENS, which is, say, very special school, one of centers of mathematics in France, and I spent 10 years in this school. Right, Burbanki is a pseudonym, is a, I would say, nickname, and the real name is some French general of 19th century. I don't frankly know, and there are only speculation why they used exactly that name, but that's less important. I think it's now this name Burbanki is associated with mathematics much more than with the military French history. Okay, so what was their idea? Yeah, it's Henri Cartan, who actually died about 10 years ago. In age, he was 104. Yeah, rather old man. So there is a kind of manifesto which was translated into English, written as evidence tells us rather precisely personally by Jean Dieudonné, and it's called Architecture of Mathematics, so you may read. But I would say it's a bit confusing because what it says that they won't really implement, say, Hilbert idea. They don't much refer to Hilbert personally. However, somehow this new formal approach of mathematics, they try to implement, right? And implement meaning that in Hilbert you don't find, how to say, application. So you have this book on geometry, but which applies to Euclidean or, say, Lobachevsky geometry, but it's not kind of geometry that you could do research in, right? It was like Riemann geometry, for example. People did new stuff in Riemann geometry, that stuff in that time, not in Euclidean geometry. And you see, so they tried kind of, as they say, apply this for. First idea was just make a textbook in analysis, but then they came to algebra, and so they covered we wouldn't say everything, however, quite a lot of mathematics. And by the way, I should mention now this project is officially continuing. Yeah, I can even, yeah. They have web page, so it looked like in 90s, it looked like it stopped. But now you see in 2016, they published a new volume. I think it's on functors. It's comprises some category theory, however, still in their style. And 2 years ago, they republished, but with new editions, so it was revised, spectral theories. And so now I think it's officially alive, still continuing. And no, probably you know they published, should be written how much? I think about 30 or something volumes. No, then there were some re-editions, new versions, so it's rather messy. No, by the way, part of it also exists in Russian. In Soviet time, they were translated. Also in English. In English, they translated actually themselves and published it in France, also in English. No, there are in my dissertation, I kind of write down all these details. I don't take my time now. Yeah, also there is seminar, you see, some new topics expected. And seminar is quite interesting. Right, so it's kind of supposed to be living existing project, even if, of course, it's their moment of their major influence. I think it's very much in the past. And it is sometime in 60s, right? So if we really count that it started in mid 30s, then I think they came to their kind of acme, high point. They came in 60s, maybe even late 60s and early 70s. Right. So one thing I would like to emphasize is this, that even if they say they just applying kind of formal approach, right? But it's not Hilbert's style approach, in fact. It's approach that can be described and was described by different people, because these Burbankists, you know, they were not much interested in logic and logical stuff. But that approach is described as semantic. And I think it's important to see this difference. And I think I can rather easily demonstrate it. No, I'm sure you know so-called axioms of, say, group theory, right? Which you may also call definition of what is a group. And that's, of course, a kind of Hilbert new axiomatic approach where we use axioms basically as definitions, right? And of course, in mathematics and algebra, as a discipline, we have, say, group theory. But now question for you, whether or not, say, do you know Lagrange Theorem in group theory? It's very, yeah, no, okay, it's very elementary, right? It says that the infinite group, if you have a subgroup, is a divisor of order of group, order of subgroup, divisor of group. Okay, very limited. But question, whether this Lagrange theorem formally follows from the three axioms in group theory, whether it's possible to reconstruct its, say, normal proof in such a way that it becomes a consequence of these three axioms, that's whatever, associativity of operation, and inverse operation, unit and inverse operation, which of course is easily formalizable, right, in first order logic.
Well, I don't sure that I remember algebra well, but I think no.
Yes, I think you are right that it doesn't. It doesn't. And reason is this, that that officially, if we take these three axioms and saying that's our theory, right? Then go ahead and interpret it as you want, right? But then every group is a model, right? So in this theory, we have no formal means, we have no resource even to talk about subgroup. You see, because group and two different groups are two different models. So what we really call group theory, and if we formalize it in Burbanki style, it's kind of model theory. It's theory of models, right? When we classify groups and doing things like this, we are working with models. And actually, this again standard definition, a la Burbanki, when we say it's a set with operations, blah blah, it's semantic in the sense that we fix interpretation set theoretically, right? We say it's a set, and then we have some notion of operation, which of course also is expressible set theoretically, and so on. So what is actually the case, that you may argue that all this theory, or that any theorem of group theory is actually provable in set theory. That you can say. No, there could be some specific problems about that. I don't know, these big cardinals or something when we come to some very specific topics. However, by and large, that is the case, right? Because what we are doing here is not just taking, say, this group theory as a pure axiomatic theory, but we are working with set theoretic models of that theory. And that's exactly why we made talk in that context about, say, axiomatic set theory as the foundation of mathematics, you see. But it's not what Gilbert actually had in mind, because he had in mind that we set out axioms and then look for interpretation and play with different interpretation. Okay, but still a theory officially, it's a kind of deductive closure, as I mentioned, right? Is what we may deduce from given axioms. And now we come to set theoretic interpretation straightforwardly. And actually what Burbanki called the signature, right, and what is still used, is very useful. So signature, no, if we say we have a, say, set and operation, and then we list axioms, right? And that's, say, signature. It's a very useful concept. However, signature is not a part of formal calculus, right? It's kind of next layer. So it's a kind of language that comprises that serves as a juncture between, say, pure logical syntax and say, semantics. And then it fixes semantics as set theoretic semantics. And by the way, they in first volume they produce their own version of axiomatic set theory. It's not Zermelo-Fraenkel. They're no, that specific topic. So it's more or less equivalent, but there are some interesting differences and nuances. Yes, but it's not pure logical syntax. That's what I want to say. Right. And as you probably know, the kind of attitude to this Burbanki enterprise, it's very diverse, because some people like it, some other people don't like it. Anyway, I think it's had an important impact on mathematical education, on all of mathematics. Interesting part of it was a attempt to introduce it really in school. Right, in United States of America, it was called New Math. You may Google New Math, and you'll find of it. And actually, it was interesting context. It was done as a response, American government response to launching Soviet Sputnik in was 53, I think. Right? Let me check again. Right. So the argument was that Soviets somehow are ahead of us in mathematics, so we should urgently do something in reforming school mathematics. So what they try to do is to modernize the school programs, and the strategy was to use some kind of baby version of Burbanki to use it in school. For example, a proponent of this was Marshall Stone, one of leading figures in mathematics of that time. And now we are talking about, yes, 50s, about 1950s. It's also interesting, and that's something I also am trying to research and understand better than I presently understand it, that it was not only about kind of formal background, not about methods of, say, introducing mathematical concepts or reconstructing mathematical concepts, teaching methods and so on, but it somehow came with certain ideology, you see? And so question is for myself, how much of this ideology is kind of contingently associated, so you may not associate, or there is kind of a deeper connection or whatever, right? And ideology was that mathematics is kind of free activity of human mind, and free in the sense that it's not related to application, to real world. So in mathematics, we are free to invent axioms, to draw consequences from axioms, to do what we want, right? And that's great because it gives freedom, and it has nothing to do with physics, with engineering and stuff. Of course, not everybody agreed. For example, Richard Feynman, who was probably, you know, right, very old, also in Institute of Advanced Studies, I think, or was he in Princeton? Yeah, please check. Richard Feynman opposed it, right? He said, no, we should really, mathematics is something which is a part of bigger picture, right? And bigger picture involves physics, involves engineering. So mathematics is somehow part of it. And even if it has some sort of autonomy, it should not be, how to say, thought and taught as something absolutely independent. Yeah, and very soon it was, they actually refused from this program. There were very interesting books by rather influential author. His name is Morris Klein. I think spelling it this. I think one of his books is even translated to Russian. It's called «Математика утрата определенности». Yeah. However, he wrote a lot. So he was a mathematician, but also very active as a, say, public figure who writes about mathematics, who also involved in this debated issue of mathematical education. And I think his paper was called "Why Johnny Cannot Add." That was against this reform. So there is also a very funny song by Tom Lehrer. No, I think I can put it. Lehrer. He's kind of a singer and with mathematical background, and that's just called New Math. You know, so it's very funny. I recommend you. So anyway, it was kind of universally recognized as a failure. And so it was abandoned. And but later, no, just a bit later, similar reform were, of course, in France itself. I think it was Lishnerovich, who was also Burbanki member, but he was one who took this job to introduce these ideas in school education. And I should say that in France, it's still preserved much more than in any other countries, this kind of Burbanki style approach in school. So I think in France was never that moment when they, as far as I know, as they said, no, we abandon it completely, as it happened in United States. And unfortunately, it happened in Soviet Union as well, because in Soviet Union was a reform somehow headed by Andrei Nikolaevich Kolmogorov, and there was some other people, Boltyansky, Vilenkin, my professor, they were involved. And actually, I think, and I was, you may call it a victim, if you like, but I think there were very good textbooks. So I studied, it was in the early 70s, 1970s. So I studied mathematics in school on this Kolmogorov's textbooks. But later, I think already in the 80s or even earlier, or late 70s was a similar fate. So somehow community of school teachers told, no, that's just not possible. And maybe indeed results were bad, but anyway, it was abandoned. And now nobody used these textbooks. Even, as I say, and that was much more balanced than, say, these American things, because at least they didn't bring that kind of ideology that it should be, that mathematics should be detached from physics or applications. It never, and there were some applications. So I don't know what was so much wrong about this, but anyway, that's what happened. Yeah, no, I think I have very little time left, and a lot of things I would like to tell you. No, I think important and interesting development in foundations of mathematics in 20th century was a line, the whole bunch of works that try to produce, say, category theoretic foundations of mathematics. May I ask you, Svetoslav and Zhenya, did you study some minimal thing in category theory? Is it now just part of your, say, standard mathematical education or not?
Very little bit.
Yes, we did in the third term, maybe.
Where?
In second course of the bachelor program in the first term of the second course.
I see. Yeah, that's interesting story. Of course, when so that idea of category and functor, it was first introduced by, here again different, but kind of firm reference, even if it's not the first, is a book by Samuel Eilenberg. And Saunders MacLean, right? Saunders MacLean. It's called Categories for Working Mathematicians, which is probably today is not the best book to start for working mathematician. because I think what working mathematician is doing very much changed. I think it was 1945. Yeah, let me. First edition. I want to check first edition. No, 71. Yeah, that was sorry. That was already later, of course, not 61. Yeah. No, anyway, when they designed that concept, that was just after the war. After the war, wow. So they written that book already later as for working mathematician. No, important things that somehow motivated. Of course, if you're doing kind of basic about category theory, it's very simple. It's, some people would say, trivial. It's a very someone called it abstract nonsense, and there are different stories who actually is the author of the phrase, but it's not. Yeah, abstract nonsense. When I studied mathematics, it was interesting because, for example, we had a course on functional analysis, and some clever student, and we had exercises, right, with Kirillov, maybe, you know, and some, but that was for seminars, which I can't remember who was doing seminars. But some clever students, they solved exercises with category theory, but somehow, you know, professor would look and say, oh, okay, but let's do it now in normal way, which is much more laborious with a lot of, you know, indexes and stuff. Yeah, but actually real power was demonstrated, I would say, in 60s. You'll find in my dissertation, if you're interested. There was a book by Eilenberg and I think Steenrode, was called something like Introduction Algebraic Topology. Yeah, but you find precise references in my book, which actually showed that this category theoretic language indeed is very useful for produce something like axiomatic theory, you know, but which would not be axiomatic in the strict Hilbert sense, and not even in Burbanki sense, but in much broader sense, in the sense that you may formulate kind of basic concepts, right, and then prove, not logically, not in terms of some formal logical calculus, but in normal mathematical sense, including so-called diagram chasing. Как это по-русски-то говорят? Нету слова, да? Ну, by diagram...
Для чего слово?
Diagram chasing, не слышали? Ну, когда мы там коммутативность всяких диаграмм проверяем, это вот так называют. Chase, как охота. Да? Вот так это по-английски.
Что-то было, да?
Да, я не знаю по-русски. Есть
гомологическая алгебра, диаграммный поиск какой-нибудь.
Ну, что-нибудь такое, да. So it was really demonstrated that using this language of categories, one may somehow improve, achieve on presenting at least certain field. And there was also a book by Mark Lane and I think Cartan. Yeah, I have these references in my book. I forgot some second author. Then was a similar thing was done here. Yeah, so So they kind of proved that that's very important language, but they didn't really think about that as a foundation or something seriously, and they didn't try to connect it to logic in any way. And a person who did this was William, or as everybody called him, Bill Lovier. Yeah. Lovier, who was a student of Eilenberg in Columbia University, but he also attended seminar by Alfred Tarski in Berkeley, where he did some exchange or something. He spent some time in Berkeley. Then he defended his dissertation already with Eilenberg. Dissertation was defended in 1964. Its title was Functorial Semantics of Algebraic Theories. And actually, Bill Lovier was first who really tried to make category theory into foundations of mathematics. You see, no, roughly speaking. So first motivation was somehow replace sets with categories, but that's of course not the whole thing. And I don't think the project should be really described in that way. But at least one thing.
Sorry, replace what with category?
No, set theory replace it by category theory. Заменить теорию множеств теорией категорий в основаниях математики.
Is it possible?
Yes. One thing, for example, that Lovier proved in this dissertation, and I think next year he published a separate paper, was a categorical set theory. That's very, very nice. So he showed how you may define what is a set by first providing some very general notion of category, right? And formalizing it with first order logic. It's rather simple. But then making some additional assumptions that say, make this category into category of sets, up to, of course, some, say, appropriate equivalence. Then, of course, there is a bunch of questions. It's not so trivial. Again, you may read in my dissertation. So there is some very general review, but then there are all references, and then you may look into references. There are, of course, so up to categorical equivalence, it's the same as, say, ZF that you obtain. In that way, no, there are still very interesting and important, say, nuances. Yeah, actually, what he, yeah, and so if you do this, you may say, okay, I may at least rewrite your set theory on the basis of category theory, right? And rather than use set theory for saying what category is, I rather use category theory for saying what is a set. And then, formally speaking, whatever you do with set theory, you can do with category theory. Yeah, however, and even you may argue that that's a category theoretic approach to sets is somehow better fits what mathematicians are really doing in practice. Yeah. You know, even there are some disagreement. For example, Sol Pfefferman was one who published a paper where he disagreed, and he argued, for example, that in order to define category, you need something like a class, at least, if not a set, right? Some notion of collection, just for saying there is a collection of objects, collection of morphisms, so you need some notion of collection first. So there are some, yeah, interesting debate, but next important development was later, was in 1970, when actually Lovier came up with his topos theory, his, or say, theory of elementary topos. Elementary topos. And elementary, it's refers to like first order, right? Yes. This idea of topos was introduced, as you probably know, by Alexander Grothendieck in 50s first. Yeah. And of course, and that was purely geometrical, so it had nothing to do with logic. And actually, at a certain point, I can't remember exactly here now, but Grothendieck, maybe it was 70, that Grothendieck made a trip. So he stayed actually in United States, and he met Louvier, and they discussed. And Louvier really discovered new thing about toposes, and that new thing was in logic, not in geometry, where or algebraic geometry, where somehow this theory of toposes naturally belonged, right? And actually, what he remarked that the topos in general, right? It's very like category of sets that he constructed in what I just said you a minute ago, right? Trying to define the concept of set category theoretically. So he noticed that basically a topos is all, no, first that category of set is a topos, but it's specific topos. So you only need to relax a little bit your concept of category of set, your axioms for set, and then you obtain category for topos. And that was, and then it's also had this geometrical interpretation. He discovered so-called truth value object in topos, so he interpreted what are truth values in topos. So he started this kind of very interesting and productive, say, interaction between geometry and logic in topos. And that was something that Grothendieck not even thought about. There are, of course, interesting, again, nuances, because this notion of elementary topos is a bit more general than Grothendieck topos. So there is a so-called Giraud theorem that, so if you study today topos theory, what you start with Louvier's axioms. And that's, you see, and that's what makes this notion of topos quite much easier, say, than it used to be without it. Right. However, it's a little bit more general, so not every topos is Grothendieck topos. For example, topos of finite sets, if you just restrict to finite set, it's still a Louvier topos, but not Grothendieck topos. Right. No, of course, I have no time. I can say a lot about this issue. I think it's very, yeah, interesting. And it's also interesting because it involves kind of unusual relationship between logic, say, and geometry, or more generally, if you like, logic and mathematics. Because I think that in a sense, it justifies this idea that geometry comes first and logic after. Because actually what happens, it's not that you simply use some external logical framework to define what is, say, topos. It's not what really Louvier was doing, but he defined what later was called internal language of topos. So there is a, say, canonical way to associate with a given topos a formal language that's kind of interprets reasoning in this topos, you see? And unless your topos is a topos of set, where your reasoning your logic is classical, so you have excluded middle and you have choice. By the way, there is a theorem that's axiom of choice in this topos theoretic rendering. It implies excluded middle in topos theory. That's
Sorry, it implies what?
excluded middle, law of excluded middle. Yeah, it's called, I forgot the name of after whom this theorem is. Giraud theorem is different. Giraud theorem shows that most of Lovia theorems, yeah, so it implies excluded middle. Yeah, you see, and that's interesting because it changes somehow status. Normally, we would think about excluded middle not as a property, right, but as kind of big metaphysical or logical principle. But here it becomes a property which actually distinguishes topos of sets among other toposes. And in other toposes, you basically have intuitionistic, no, at least propositional logic associated with every object of this topos. So it also becomes kind of typed. So if you now think about each object as a, say, particular type, and then no, that's how it's usually done. Then you may interpret not only locally your, say, intuitionistic calculi, but also globally. And of course, this global aspect, which is really, really interesting, becomes really interesting in topos theory. Right. Yeah, and I think it's really kind of changed a little bit idea of what is axiomatic. It was never officially recognized, say, by Bill Lavia. Even I discussed with him this point a lot. He kind of, he didn't disapprove, put it that way. Right, so you can read it also in my dissertation. Yeah, our time is and then of course there was this later development with the Voevodsky univalent foundations and stuff, but I think I have no time, right? Time is over. No, okay, let's keep it as a maybe future possibility. Maybe I can give a talk on that, because I think it's really something new and interesting and worth working on and continuing. Yeah. No, if you like, we may arrange just in our course. I can talk about this. But now, if I understand you don't have time, right? Or if you may stay another half an hour, I can do it now.
Sorry, I haven't time.
Yeah. I know. Yeah. No, okay, let's. Yeah. Ну, так, что-то в чате. Is it possible to arrange? Сейчас. Ну давайте. То есть вы говорите о том, Святослав, чтобы не делать нам в один день все доклады, а все сделать 18-го?